Alright, hello everyone. I have no idea why only, I was gonna say I have no idea why only one screen's working. It blinked at me. Don't know what that means. I'm a little afraid to hit the power button, but I might. Oh, that turned it off. We're gonna hope that that'll also turn it back on and turn them both on. If not, I'm gonna have a great time up here. Maybe I should have, look at that. Alright, that's fine. While this is doing things, I can go ahead and update you all. So I sent out the detail about the iClicker, and I've already got a few questions, which is always good because that reminds me of things I should mention to you all. So just recapping things, remember, you can buy a physical one or the digital one. They have trade-offs. The physical one is forever. You know, if you have another class that uses the physical iClicker, you'll have it. But I have no idea if you're going to have other classes with physical iClickers, so that's a toss up in the air. The digital one, the benefit of the digital one is that you can use it remotely. So if you decide that you're going to tune into my class remotely, then great. You can do that with the digital one. The downside to that one is the $15 thing only lasts for the semester. So, trade-offs. Pick your poisons. Either way, you're out of pocket maybe $15 for this class. It's not ideal, it's not $0, but it's cheaper than a phone, by far. So, there's that. If I could make it free, I would, but I haven't found something that works as well as iClicker for as low of a price. That was kind of the cheapest thing I could find that accomplished my goal of getting feedback from you all during class, giving opportunities for you all to practice stuff and actually seeing what your responses are. When there's 200 people, that is a precious commodity, and so they charge for it. So, with that in mind, today there will be questions that pop. I will be using the iClicker system. I sent out an announcement saying that grades for iClickers will not start until a week from today. That is true. So, the 29th of August is when the iClickers will actually start counting towards your grade. However, I will ask iClicker questions today and Tuesday, and I will upload those scores for the only purpose of showing you whether or not you're registered correctly. That is the reason for that, because there's two hurdles here. One, you need to make sure you get registered to the class through iClicker and be able to see the stuff there. The second is making certain the grades sync to web courses. As long as you are registering on that using the link I have, the first one should be resolved. And as long as you're using your UCF email, that's your NID, that thing, then you should be fine as far as it transferring over. The first step is the most important. As long as you're registered in my class, we can always fix the second one in the future. But if you're not registered, you might end up losing points. And the reality is, so Thursday they're going to start counting. So I'm going to give today, and I'm going to give Tuesday. It's kind of for you to check, and after that, it is what it is. If at any point iClicker does not capture your response or anything like that, you need to let me know as soon as possible, because if you wait till the end of the semester and say I've been in class the entire time and responding and it didn't record anything, there's not much I can do unless I really know your face for some reason, because I have seen you and all that kind of stuff. So if you're lucky, I'll recognize you. If you're not lucky, it's one of those, if I don't have a record of it, there's not much I can do about that. I can't just skip. But again, at the end, I calculate the grades with and without, so there is kind of some stuff there. But at any point, if your thing isn't working, you come and let me know kind of ASAP. Email or after class, anything like that. My emails tend to get, in the beginning of the semester, all my emails are iClicker related, and that's okay. I'm happy to help you all with that, but register as soon as possible. Make sure you use your UCF email, and 1 month from now, your free trial will run out. Make certain you actually pay for the subscription before that 1 month trial, because say you sign up literally during class today, 1 month from now could potentially be in class, and then it fails, and then I also get a million emails. So that's kind of the two major complications I had last semester, and if I can avoid that for as many people as possible, that would be excellent for me. I am happy to respond to emails, but if I can avoid responding to the same thing a million times, it's good for me and it's good for you. Yeah.
How is that coming at physical iClicker?
Yeah, so I got a little box here. I have a little receiver here that picks up your signal and transmits it to my computer, so if you have a physical one, it should work. We'll find out like you'll see today. Depending on which model you have, the question is how do you know whether or not the response went through? Some of the newer ones will get a little check mark. If they don't, you can always go into the app after the class and kind of see did it give you the points. The points for each day will show up on the iClicker website/app. Was your question about registering it or? Yeah, so registering it, you will need to make an account. And then either in the app, potentially online, definitely I know on the app, there's a place where if you have a physical iClicker, you'll register through there. So you'll still use my link to get connected to the class, and then you will go through the app and find a place that says register physical iClicker. And that'll be the solution to that. Yeah, that's a good question. Good news, if you have a physical iClicker, and if there is any complications with getting registered to the class, it will still record your stuff. It just won't know that that's you until you make that registering happen. So those things still kind of record. Any other questions about this? All right, great. It's going to be a good time. Again, these are valuable. They're useful. There's a reason I do them, even though they are more headache for me, and even though they cost a bit of money for you. So, getting into things. Our goal is to get through the rest of this PowerPoint today. Shouldn't be too bad. There's really not that much in it. Last class, we went through the syllabus. If you missed all that, please check out the live stream, the video I posted. So remember, every class is live streamed, so check that out. Also check out the simple syllabus. Both are good. Pretty much anything you need to know will be in there. So keep that in mind. One thing I didn't mention, one of these Thursdays coming up, we have a football game, so we won't have class that day. It's like all classes after 2:30 are canceled. I forget, does anyone know exactly what day that is? 29th, so it's next week. Yay. So, okay, I guess attendance, okay, I said grades are going to cut next Thursday. Clearly not, because we're not going to have class. How are we going to resolve this? That's something I need to think about, because one class may not seem like a big deal, but it will result in us getting a little bit behind and having to rush a little bit more. So I'm going to think about it. It might end up being, I post a video kind of going through the stuff. I know that's not ideal, but the reality is I kind of don't really have a way to get through the same amount of content otherwise. And at the end of the day, I'm not the one that decides what we have to get through. It's kind of, this is a course, there's set stuff I have to get through, and if we lose a day like this, the other classes didn't. So it's not like I can just not test you on as many things and not assess that. So it might just end up being the video for kind of the class will be posted, and then you can ask me questions or email, office hours, that kind of stuff. Not ideal, but it might be what we have to do. Yeah?
So when we saw the discussions in the school board,
no, any lab, discussion, class, anything after 2:30 is canceled on that day because of the football game. So that applies to all the things. But in our case, yeah, it's probably going to be, I'm going to say, hey, here's the video from last year, kind of where I went through the stuff. Refer to that, solve things, because the reality is I don't really have a way to, the test date's kind of set, and I can't really bump it back a week because it affects everything else. I have to cover the same amount of stuff. It's the restrictions, but it is what it is. It's not fun, but that's how these things go. All right, but I have office hours, so come by and visit me. Anyhow, so last week we talked about syllabus, we talked about structure. I then started to talk about the metric system and how awesome it is. This is going to be one that we just kind of get familiar with by using it. So we're going to learn the unit conversions, kilometers to meters to millimeters, really by using them. Really the only things you need to know is kilo, the base unit, milli, and centa. Those are really the ones that people actually use. At some point when you get to Physics 2, you'll work with micro and nano. But in this class, kilo, milli, so we can see them in this slide here. Oh, did we do this problem? No, I don't think we did. All right, we ended with what is 3. So, actually, I said we did the metric system. We didn't really get too much of anything. We talked about problem solving process. All right, great. Spend 30 seconds. What is 3? Come up with something in your head. What is 3? Just think about it. It's probably a question that sounds stupid. What is it? Yeah.
3 is a number after 2.
That is a fact. 3 is a number after 2. Any other thoughts? Yeah.
A sig dig.
A sig dig could be. Yeah. How many sig digs would? The magnitude. Very nice. Oh, yeah.
There's not enough information.
Not enough information. All these answers are correct. So the reason I asked this question is because you're going to work with numbers in this class, just like you did in the math class. You're going to do a lot of math in here. But the major difference is in math, you saw the number 3, and you did stuff with it, you didn't really think about what it meant. You did 3 plus 2, and you got 5, and you said, great, I did it. You didn't really concern yourself with what it was figuring out. It was just logic, pure logic. In this class, numbers need to mean something. So the question is 3 what? And the answer to that is, it depends on the unit that comes after it. In this class, if you don't put a unit after it, it means anything. If I told you I lived 3 away, 3 miles, 3 centimeters, 3 minutes, 3 hours, it could be anything. If you don't put a unit, the number 3 can mean anything. It's an amount of something. We put a unit after it to tell us what? 3 kilograms, 3 seconds, 3 meters. Very, very important. Because in this class, the math means something. You're always calculating. Physics is using math to understand the real world. In the real world, the number needs to mean something. It needs to represent something. This chart down here is the unit conversion, so you do not need to memorize it for a few reasons. One, we're not going to use most of it. It's kind of tricky to see here. Let me make this thing bigger. Figured out a way that I should be able to present in this mode, but we'll see. Oh, look, a squirrel. My desktop just randomly picks backgrounds. That squirrel has no significance other than that's what Microsoft decided. So if you try to read into that, you're not going to figure out too much. All right. So here's all the different prefixes. So we put prefixes in front of units because if I asked you how many, let's put it in a unit you're familiar with, how many inches away your home is, no one's going to, if you know that off the top of the head, that's very interesting that you do. And I'd be really interested to know why you know that. But you don't. People don't count large distances in inches because it could be like 3,500,000, like it's a huge number. And our brains can't conceive huge numbers. If I told you there was 3 million people outside, that's just like, if I told you to imagine 3 million people, it's going to just be a massive blob of people. 3 million people and 5 million people, you probably wouldn't be able to distinguish between the two unless they're right next to each other and said that's bigger than the other. Our brains, and this is an interesting kind of psychological thing you can do. The way I do this is I try to imagine what's the biggest crowd of people I can imagine where I can actually treat each person as an individual. Where I can actually imagine each person as an individual and it's not just a mob. In my head, that's maybe 1,000 to 2,000 people. It's kind of in my head where I could imagine that many people and I could go through and kind of assign that. Once you get beyond that, it just becomes a blob. So we use prefixes to change the number to something our brain can conceptualize. This is purely a psychological thing. Because if someone tells you that they live 3,570,000 inches away from here, you're going to say, I have no idea what that means. If they say 5 miles, you can imagine that number. So it's an interesting kind of psychological thing, and it's relevant because if someone wants to explain something to you, you need to understand what they're saying. So the way we do that is we either multiply or divide by these ratios shown on the right. So you can see here if we want to go from kilometers to meters, we're going to multiply by 1,000. If we want to go from meters to milli, we're going to divide by 1,000. And you're going to see this kind of here. Scientific notation is going to come up in this class a lot. So 3 times 10 to the minus 3, that's 3 millimeters into meters. So 3 millimeters is the exact same as 3 times 10 to the minus 3. And something I want to show here is I will not be using this 3 times 10 to the minus 3 notation very often for a few reasons. It's fine, it works, it's what a lot of people use. It's a pain to format, for one, it's a pain to type. The second is it takes more space, and the third is it sometimes isn't what your calculator shows. I'm going to use this notation in this class. You'll find that different teachers use different things. Depends kind of where you go. I'm going to use this 3, capital E, minus 3. It means the exact same thing. It means 3 times 10 to the minus 3. It is shorter to write. It is way easier to format. And for a lot of your calculators, this is what it's going to look like when you use scientific notation. There's like an EXP button or a capital E button. Depends. Some calculators do use that times 10, but a lot of them use this E notation. And so because of all those reasons, it's my preference. That's how you're going to see me exclusively basically using scientific notation in this class. It's short, it's quick, it's easy, it's nice. I love it. There's no superscript or subscript. It works great. So, bam, there's this. You're going to get so much practice with this. We're not going to really bother spending a ton of time today on it. We will talk about it and we'll do a practice one here or there. But almost the vast majority of problems in this class, you're going to have to do a unit conversion. So just by nature of doing unit conversions all the time, you're going to get really good at it. Because we have to work in the base units. All our equations are calibrated for base units. So what are the base units for various things? For length, it's meter. For time, it's seconds. Current, it's ampere. Anything you want to measure has a base unit. They all lack a prefix except for mass, which uses kilogram, which is funky. I don't know why they didn't use gram as the base unit, but it's one of those someone decided at some point, and here we are. So kilogram is the base unit for mass. It does have that prefix meaning 1,000 grams, so kilogram. You probably already know that, but it is just an interesting thing to note. All the others, no prefix. That's how you know it's the base unit. Mass is the only one that kind of throws things off. It is what it is. But again, the beautiful thing about the metric system, the prefixes make things so easy. And think of the imperial system. That's the one that we use in the US. It's not great. Engineers, you're going to have to be familiar with both. You're going to have to both know the imperial system, inches, feet, pounds, and you're going to have to know the metric system. And you're probably going to have to, if you've ever worked with tools, you often have to have both sets of tools, because depending on where you buy stuff, it'll either be in inches or it'll be in millimeters, and it's great. Our system is not great, but it would cost a lot of money to change. Imagine if they tried to change every single mile per hour sign to kilometers per hour in the US. That's an insane amount of signs that would have to change, and there's many more things than that. But yeah, there's only 3 countries. Myanmar is one of them that uses the imperial system. Us, some country in Africa that I forget the name of. I think maybe Liberia. Everyone else in the world uses metric system. As engineers, if you're an engineer in the US, you will have to use both. Woo! Metric system is better though. Easy proof of that. Convert 5 miles to inches. It's not easy. If you can do that in your head in 5 seconds, good on you. I can't. If I want to convert 5 kilometers to millimeters, 3e to the 6. I did it. It's so easy. There's 1,000 kilometers in a meter. There's 1,000 millimeters in a meter. So 3 times 10 to the 6, I just converted 3 kilometers into millimeters, and that took me 5 seconds and about an inkling of brain power. Whereas inches, miles to inches is, you need a calculator. 5,280 times 12 times, no, I think that's times whatever the number is. Trash. Oh, well, that doesn't make any sense then. That's what happens when you don't use enough brain power, when you get too confident in your abilities. Thank you. You will see me make stupid mistakes like this all the time. And these are always good opportunities to remind you all that you will also make stupid mistakes all the time. We're in good company. There's one thing we all have in common. We're human beings. Human beings, there is no perfect human being out there. If you find one, great. They are then the standard for perfection, I guess, because no one else is. Good luck finding someone. You will make mistakes. It's all about reducing those mistakes and making sure those mistakes aren't catastrophic. This mistake didn't cost me too much except a little bit of my pride. I'm okay with that. But in your case, in this class, you make a mistake, it affects your grade. Probably won't affect it that much. Future things, it will make a big difference. So get into good habits now to avoid making mistakes. Because if you get, for example, write stuff down. Do not try to hold everything in your head. Otherwise you will, look, they were able to identify because it was written down. I don't know. Whatever. All right, fantastic. First clicker question. What is 38 kilometers in meters? Boom. It's going to send a picture to your all's devices. The other benefit of the digital one is it sends a picture to your screen, which is maybe handy. If the font's too small for you to read, it's probably still hard to read on there. So, yeah, you got a few moments. Try it out. This is also going to show me how many people have signed up for clickers. math here is really easy because it's metric system, i.e. best system. We'll go to a minute 10, 15 more seconds. Yeah. The code or the frequency A. Always A. Good question. All right, we'll close this thing out in 5, 4, 3, 2, 1. So it is nice to see how many people have either registered or done something. You can see how many responses here. In the future, as more and more people get registered and as my class gets a bit more stable and how many people, this also kind of gives me a measure of how long it takes people to solve it and all that jazz. If this number was still ticking up, I'd probably give more time. All right, but I'm not going to. It's over. All right, fantastic. So what is 38 kilometers in meters? Let's do the easy way. Let's go ahead. 38 times, so there's 1,000 meters in a kilometer. So something to keep in mind here. Always the question with unit conversions is, do I multiply or I divide? Generally, people remember, so in this case, people remember that it's 1,000. There's 1,000 kilometers in a meter. And often the question is, do I multiply or do I divide? And the really easy check here is what makes sense. We know that so meters are smaller than kilometers. So when I convert this to meters, I should get a lot of meters. So I should multiply by 1,000. There's 1,000 meters in it. 1,000 is the exact same as just putting times 10 to the 3. 1,000 is 10 times 10 times 10. So boom, there's the answer. Oh look, there's that answer. Let's look at the other ones here. If you didn't realize this, so this answer is the same as this answer, just two different ways of writing it. If you shift this decimal place one more over, this is also 3.8E4 meters. So great, it's also this one and that one. They're all the same. All the answers are right. Boom, boom, boom. All right, fantastic. This is not something I do all the time, but I purposely did it for this problem because you get common questions like, how do I want the answer? So there's going to be a free response part of the test, and the question is, how do I want the answer? Any of these would be fine. I do not care how you write the answer as long as it's correct. Now, I say that a lot of your stuff will be multiple choice. So, if there's one right answer, you do need to recognize that all 4 of these are the same number. That is a skill, is to be able to take your answer and recognize that even if it doesn't look exactly the way you wrote it, say you found it was 38,000, but one of the only answer was 38 times 10 to the 3, then you recognize those are the same thing. That's a skill. So, on the free response, I don't really care, but you still need to be able to recognize that these are all the same because on the multiple choice, it might not look like the way that your calculator spit out. Now, I will say I don't really care with the caveat. I don't want to have to, your grader doesn't want to have to count a bunch of zeros. So like that can be, if you ever have a big number, it is nice to put in scientific notation. Say the number was something ridiculous like 6, 7, 3, 2, 5, 2, 1, 162. If you put the commas there, it makes it easier. But you know what number's a lot nicer to look at? 6.73E9. That's a much nicer number. Also didn't take as long to write. There was some rounding, and depending on what we're doing, 2 or 3 decimal places is a good rule of thumb, because when it comes to problems in this class, as long as you're within 1 to 2% of the right answer, you're doing, like, that's good for me. Depending on your job in the future, they might need more precision than that. But in the case of our class, I care about the process, and you cannot get within 2 or 3 decimal places of an answer. You cannot get within 1 to 2% unless you did it correctly. So, anyway, something to keep in mind. Rules of thumb. All right, so this is one of those questions of, remember I told you all, when you convert, do I multiply or do I divide? This is one of those cases where if you think about the logic, should I get a lot? So it says how many milliseconds are in a minute? And so the way you figure out whether to multiply or divide, is there a lot of milliseconds in a minute? Or is there very few milliseconds in a minute? And that helps you decide whether to multiply or divide by whatever numbers. little longer. And if you know whether there's a lot or a little, it automatically will kind of point you in the direction of a couple answers. So that's also handy. All right, we'll go to 120. Close this out in 5, 4, 3, 2, 1. All right, so thinking through this, how many milliseconds are in a minute? We first have to convert minutes to seconds. This is one of those seconds and minutes and hours are the one kind of units that don't work in that nice base 10 system. But the entire world does at least use the same system for this, so trade-offs. All right, so in 1 minute, there is 60 seconds. We did it. We got seconds, but that's not the question. The question was how many milliseconds, and this is one of those cases where people can get mixed up. Do I multiply by 1,000? Do I divide by 1,000? And again, you just ask yourself, you don't have to remember exactly whether to multiply or divide. You don't have to set a bunch of math, you just have to say what makes sense. Should I have a lot of milliseconds in a second, or should I have a few milliseconds in a second? You should have a lot. There's 1,000 milliseconds in a second, so I should make this bigger. How do I do that? Multiplying by 1,000. So that's going to be 60E3. That's not an option, but 6E4 is, and these are the exact same thing. So again, some good practice of recognizing that the answer you want might not look the way you have it writing. And you have to realize that these two are the same thing, and it looks like the vast majority of you did, so great job. But yeah, my brain is not great at memorization. I don't have much memorized, but if you can think about what makes sense, that'll sometimes get you past having to have things memorized. I do have memorized these conversions because I've done them so much. You will end up doing that too, but you might get mixed up on whether to multiply or divide. I do that at least. And I have to think through the logic. All right. So this one, I'm going to work through. Car is traveling at a speed of 120 kilometers per hour. What is its speed in meters per second? This is a problem from the problem set. Reminder to y'all, the problem set is your kind of go-to place for preparing for this class. I do not grade the problem set. I will never know if you do the problem set, except if you don't, you're probably going to worse grade the class. Like, that is the reality. That is the things you want to be practicing. This is one of those problems. If you do poorly on a test, my first question will be, did you do these problems? So, here's one of them. We are going to go from, so let's go through the problem solving process. What's given? We have 120 kilometers per hour. Step 2, what are we trying to do? We are trying to convert from kilometers per hour to meters per second. 3, how are we going to do that? We remember that there's 1,000 meters in a kilometer, and then we remember there's 60 seconds in a minute, and we remember there's 60 minutes in an hour. So we're going to do the easy one first. So we'll go kilometers to out, we're just going to convert those two. There is 1,000 meters equals 1 kilometer, 60 seconds equals 1 minute, and 60 minutes equals 1 hour. And again, we end up in one of those situations. Do I multiply? Do I divide? You can start to see how it can get easy to get this stuff mixed up. We're going to do the easy one first. The easy one is converting from kilometers to meters. I have 120 kilometers per hour. Should I multiply or divide? Well, if I'm going 100, think of what kilometers per hour means. This is kind of a good preview of what we're going to get into next week, 1D kinematics. Just say it, kilometers per hour. It literally means in 1 hour, I go 120 kilometers. It's how many kilometers I travel per hour. If you're traveling 60 miles per hour, it literally means I travel 60 miles in 1 hour. So thinking of this, if you travel 120 kilometers in 1 hour, you are traveling a lot of meters. in that hour. Not a little bit, you're traveling a lot of them. So we're going to multiply this by 1,000. And I will put the units here to show you that, why that works out. There's 1,000 meters per kilometer. The units cancel, and great, we get 120 E3 meters per hour. That's the first half done. That's not what we want, but that's at least part of the process. 120,000 meters in 1 hour. That's a lot of meters in 1 hour. Now, we know we're going to either have to multiply by 60 or divide by 60, and then we're going to have to do that again. And again, you could think about setting up the math and doing none of that, or you could just logically think through what makes sense. I travel a lot of meters in 1 hour. I travel a lot of meters in 1 hour. Am I going to travel a lot of meters in 1 second? Or am I going to travel not as many meters in 1 second? That's the thought process I use to determine whether to multiply or divide. Or if we break into pieces, every minute, am I traveling a lot of meters or not that many meters? Well, if 1 hour I'm traveling a lot, and 1 minute I'm not going to travel as many. So, we're going to take that 120 E3 meters per hour, and we're going to recognize that we are not going to multiply by 60. We're going to divide by 60. And we're going to divide by 60 because that's going to let us kind of work things out. There's 60 minutes per hour. And the result of that is these hours will cancel. So you can see it mathematically, but the reality is I'm making up the math based on the knowing it needs to get smaller. Every minute I'm not traveling. I travel less than a minute than I do in an hour. Hopefully that's obvious to you. If you're driving your car, you get much farther when you drive for an hour than when you drive for 1 minute. That's the logic I'm working with here. So, this math I can do in my head. This is what 9 years of physics gets you. That's how many meters I travel per minute. Same exact logic, we'll repeat again. In 1 second, am I going to travel more or less than that? I'm going to travel less than that. So we do it again. This one I can't quite do in my head. At least I'm not going to risk it. I know this answer only because I taught a class before this where we had to utilize this. You are my second class that I've gone through this with. But you want to use a calculator anytime stuff like this comes up with. If you try to do this in your head, you're going to make a silly mistake. I know this because I've made a lot of silly mistakes. I am not doing this in my head, y'all. I am not doing 2,000 divided by 60 and, wow, Dr. James is so good, he can do this in his head. No, I answered this on Tuesday with my studio class. And I just remember the answer because I saw it from like 50 students. If you asked me from a week from now, I wouldn't remember the answer. So, do not see me and say, wow, I should also do this in my head. That's a smart decision. No. Plug it in a calculator. Your calculator won't do you wrong. Your brain will. All right, 33.33 meters per second is the final answer. And this gives me a great opportunity to teach you all a nice benchmark. And I'm going to mention this benchmark a few times. We're going to see meters per second a lot in this class. And if you have a good feel for how fast 33.33 meters per second is, you have a better feel for it than I do. I don't work, even though I do physics every day, I'm not measuring things in meters per second. I drive a car. My car says miles per hour. I know how fast 30 miles per hour is. I know how fast 60 miles per hour is because I experienced that. My car doesn't tell me meters per second. So how do you actually make these numbers make sense to determine if your answer is correct? I have this handy, so I've just looked this up before because I was curious. 60 miles per hour is 27 meters per second, roughly. This is a fantastic thing to have memorized. Again, memorization, I try to avoid it, but this is so handy. Why is this useful? Remember in the problem-solving process, step 5 is does my answer make sense? If you don't know what if you don't work with meters per second all the time, you can't really figure out if that makes sense. So let's give an example. Say you're solving a problem about someone walking. And I give you a bunch of stuff, and you do a bunch of calculations, and you calculate that the person is walking 30 meters per second. And you say, I don't know if that makes sense. That is faster than 60 miles per hour. 30 meters per second is bigger than 27. No one is walking faster than 60 miles per hour. That is why this is useful. When you're working with problems and you're actually calculating things, you need to evaluate whether that's reasonable. If it's not reasonable, you messed up, or I wrote a really crappy problem. I've already gone through this class and kind of done the problems and checked them all, so I can tell you that they should be reasonable. A car would make sense to go 30, like in this problem. A car is traveling a little bit faster than 60 miles per hour. That's very reasonable. What if instead you calculated that the car was going 100 meters per second? 27 fits in that about 3 times. That's saying the car is going 180 miles per hour. Probably a little too fast. Most cars aren't going 180 miles per hour. So, anyway, great skill to have. Calculators can solve things, but can they decide whether or not the answer is reasonable? No, that's up to you. You have to do that. It's what you sometimes get paid in a job for. Can you make those decisions? All right, great. Units, all that kind of jazz, done. You get lots of practice. The problem said, on to vectors, i.e., we're going to begin our love-hate relationship with right triangles. Vectors, they're a good time. I remember learning, this is one of the few things, I remember learning about vectors being like, not really understanding what they are. It's this. It's an arrow. That's what a vector is. Sounds stupid, it's an arrow. There's 2 qualities an arrow has. You can measure how big the arrow is, and you can see which way it's pointed. That's what a vector is. It has an amount and a direction. So this arrow, let's just make up a number for it. Let's say it's measuring velocity. Vectors, various quantities are vector quantities. Velocity is one of those. Acceleration is one of those. Force is one of those. Anything you want to measure, where you not only want to know how much, you want to know in what direction. And direction matters. You're not going to get to Tampa if you drive north. Direction matters. If I throw an object to that side of the room, well, if I throw an object to that side of the room, everyone on the right side of the room has to be concerned, the left side of the room doesn't. Direction matters. So when we're solving problems, we need to know direction. If I push this desk forwards, it goes forwards, and that matters to the people that it's directly in front of. It'll eventually hit. Your rocket needs to be pointed up. Like, there's all these examples that are obvious when you think about it, why direction matters. It makes problems more complicated, but look, I don't get to decide how the world works. I just get to teach you all how to predict what's going to happen, and you have to account for direction. You have to have an amount and a direction for certain things, and if they have this, you have to do certain math corresponding with it. So again, just making up numbers. Let's just say this is 10 meters per second. It's 45 degrees. If you toss the ball, it's going to go up, and then gravity will pull it down. You can kind of predict what's going to happen. The experience would be way different if that ball was pointed straight into the ground or whatever. So, the rest of the class is just practicing how to work with vectors. And I'm going to show you all what you need to be able to do with them and all that kind of jazz. You're going to get lots of practice with them as well and develop a love-hate relationship. The world is in 3 dimensions. So we need to recognize that, and therefore we can break them into the X direction, the Y direction, and the Z direction. You all will be fortunate that we'll basically just keep things to 2 dimensions, because if you can do it in 2 dimensions, basically the same rules apply to 3 dimensions. It's just extra math for the sake of math. So we'll largely just keep things in 2 dimensions, but the reality is, in the real world, you will have to account for that 3rd dimension and have to do extra math. Notation-wise, we're going to say I is the X direction, J is the Y direction, and K is the Z direction. This is just common notation. In your future classes, this is the notation they will use. You will sometimes just see them. So this one down here says the vector A points 8.66 in the X direction. So 8.66, this X just says in the X direction. This is the same thing. Plus 5.00 in the Y direction. These are called unit vectors, these little triangles. They just say which way it points. It points 8.66 in the X, and it points 5 in the Y. So in practice, what does that mean? How do I actually draw this vector? It's got 2 numbers to it. We draw an arrow. So this 8.66 is in the x direction. It's positive. Positive is to the right. Negative is to the left. It's exactly what you'd want it to be. Positives and negatives will matter. So we draw an arrow. That's 8.66 to the right because it's positive. We then draw another arrow that is 5 pointed straight up. So we're going to draw an arrow that's pointed straight up. It's a little bit smaller. So y direction is up and down. Positive is up. Negative is down. We'll make a nice little table of that over here. It sounds obvious, but trust me, you will forget this at times. So positive is to the right. For the y direction, it's up. Negative is to the left. You'd be like, duh, obvious. You will forget to do this in problems. You will have something downwards and you'll put it as positive. You'll have something to the left, you'll put it as positive. So, it will happen to you. It's happened to me. All right, great. We draw a vector that's pointed up. And so what is the direction of A? We start at the beginning. We find the end. Boom. There's A. The direction of A points to the right. How much does it point to the right? 8.66. It points up. How much up? 5. Ta-da, we made a right triangle. You're going to make a lot of right triangles in this class. A lot of them. You will get really good at trigonometry. And if you don't like it now, well, you're going to have a terrible time if you take statics. Statics, you're going to be doing all the vectors, all the components. No matter what y'all do, unless you're a chemistry major, then you're spared. There's not really much vectors probably with chemistry stuff. But the rest of y'all, you got to suffer. All right. So, there's that. And you know what? If we wanted to make this, so at this point it's just numbers, let's make it physics. Great, now it's meters after everything. This would tell you where you're located, for example. I'm located 8.66 to the right, 5 up, bam, that's my location relative to some origin. All right. So, kind of already said this. You draw the one on the bottom, you draw the one on the side, and you get that. That's, I already went through that. So this is nothing new. All right. The other piece of this is the angle. So there's two things we can find in this triangle. Let's just draw the exact same triangle. 8.66 this way, 5.00 up. We get our triangle here. There's a few things we might want to know about A. We might want to know, so for example, let's say this is position. We're going to talk about that stuff next week. So 8.6 is the right, 5 up. How far am I actually away? How far away from here to here? It's a right triangle. Hopefully you remember Pythagorean's theorem. If not, you will remember it by the end of this class because you're going to do it a lot of times. A squared plus B squared equals C squared. So if we want the value of A, we call this the magnitude of A. This is the notation you'll see. The magnitude of A is how big A is, with no direction associated with it. And that will just be the square root of 8.66 squared plus 5 squared. And the easy way to check your work here is whatever I get should be bigger than 8.66. Anytime you find the hypotenuse is the biggest side of a triangle, that is a... So remember, step 5, does my answer make sense? If you get a number smaller than 8.66, you probably just hit the wrong, like you plugged it in wrong in your calculator. That's fine. Better that you recognized it than you get the wrong answer. It's always good to kind of realize, how can I see if my answer makes sense? Oh, look at this. It's so nice. It basically rounds to 10. 10 is bigger than 8.66. Yay! That's a good sign that we did something correct. All right, great. That's one thing that we would want to know about a vector. How big is that vector? Based on the x and y components. The second thing we're going to want to know is the direction. Remember, direction matters. Am I going left? Am I going right? If I'm going up, how much up am I going? It matters a lot. I can't stress how much this may seem tedious, and this may seem, why are we having to do all this math? You have to know which way things point. You have to know which way forces are pointing. If you're building a building, you need to know which direction all the forces are going to make certain that they all add up to 0. Because if they don't add up to 0, that building is going to get pushed over, like it's going to experience a force that's going to cause it to want to move in a direction. And that's probably not something you want to happen. Or if it is happening, you want to make certain you can counteract that. So, direction matters. All right, so how do we find this? It's a right triangle. If you all don't remember this, you're going to use this a lot. SOHCAHTOA. Memories. Right? Brings back memories of whatever class you first heard that and heard it a million times. SOHCAHTOA, if you don't remember it or you don't know it, sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. Tangent of theta is opposite over adjacent. How do I find the angle? We actually have all three sides. We just calculated it. This side's 10 meters, so pick your poison. You could solve for the angle with sine or cosine or tangent. All of them work. I'll prove it to you. Let's use sine. Sine of theta is opposite over hypotenuse. I am solving for the theta here, my opposite. So rearranging this, it's going to be sine inverse of opposite over hypotenuse. Opposite of sine is sine inverse. Sine inverse, what's my opposite side? 5 over hypotenuse is 10. Boom, plug that in a calculator and you get a number. It's going to be between 0 and 90. It's going to be less than 45. Sine inverse. 5 divided by 10. 30. 30 degrees. Now, there's a good, so I'll come back to something, but for now I want to prove to you all, you could also have used tangent. Tangent is opposite over adjacent. Therefore, theta will be tangent inverse of 5 over 8.66. You plug that in a calculator, and it will also give you 30 degrees. As long as you're following the right logic, you should always get the same answer. You're going to find this class there's multiple ways to get the same thing. I'm just doing this because it was getting a little laggy, and I think it was because all the writing makes my computer stressed. So just save it real quick, makes it a little bit less stressed. All right. Now, your calculator might have spit out a different answer. It might have spit out, I think it's like 0.12 radians. I don't have that memorized. That's just, again, Tuesday class. Depending which one's right, 30 degrees or I think it's 0.12 radians, they're both right. It all depends what mode your calculator is in. This is something you got to be careful of. We will largely be working with degrees in this class. We might work with radians here and there, and you have to know when to use which, and I'll kind of give you a heads up when we're switching and why we're switching and all that. There's two ways to measure angle, and they both have their benefits. Radians is superior because radians actually mean something. There's 2 pi radians in a circle, and how do you get the circumference of a circle? You multiply the radius by 2 pi. You multiply the radius by the radians of a circle. If you want to know the arc length, so the length of a quarter of a circle, you multiply the radius by pi over 2. The amount of degrees for that. Anyway, we'll see that eventually. Degrees is beneficial because if I told you 0.12 radians, I don't know what that means. Is that like a lot? Is that a little? If I told you 30 degrees, you kind of know how big that is. Trade-offs. Alright? Degrees, people are familiar with. Radians actually has a mathematical meaning to it. I did learn, fun fact, that 360 degrees comes from, and again, I'm just hearing this from a student, I haven't fact-checked it, but it makes sense, roughly how many days are in a year. So that's kind of interesting. That's where that number kind of comes from. Maybe. Have to fact-check it. Check it for yourself. All right. Okay. I'm going to open this question, then I'll read through it, and then I'll tell you all how to solve it. Which of the following shows the vector negative 15.79 I hat plus 12.04 j hat? Remember, to the right is positive, to the left is negative. Up is positive, down is negative. You can also do math. There's 2 ways to do this. There's a quick way and there's a math way. They both get you to the same answer. Oh, and to read out so we have vector A, which is pointed up and to the right. We have vector B, which is pointed up and to the right. Vector C, which is pointed down to the right. Vector D, which is pointed up to the left. And F, which is pointed down to the left. All right, we'll go to 2 minutes. Give y'all 20 more seconds. So I'm going to draw a vector. This is the x component. This is the y component. I need to remember the plus or minus matters. So this says negative 15.79. The negative matters. That means I need to draw an arrow to the left that has a size of 15.79. Drawing a picture is always recommended. I cannot stress how important it is to draw a picture. If you don't learn it now, you will learn it eventually. It's one of those, why try to hold it in your head? Like, drawing a picture is just so useful. You'll see me do it in problems. When I solve problems, I do it. Anything I'm telling you all to do is something I do. So, just keep that in mind. If it's good enough for me, it's good enough for you. All right, great. So it's to the left 15.79, and then I'm going to go up 12.04. When you're drawing vectors, make certain it doesn't need to be perfect. Ugh, my lines here are wiggly waggly, whatever. It's fine. My vector that's 12 should be slightly smaller than one that's 15. Try to, you don't need to be perfect, but, just keep that in mind. So that's slightly smaller. And I'm going up because it's positive. And so the end result is that my vector is going to go from here to here. And I need to move this over 15.79. So great, we get a vector that is this way. It is pointed to the left, and it is pointed up. There is only a single vector on here that is pointed to the left and that is pointed up. It's this one. The answer is D, which we largely got. Great job. And if you did the math, you could confirm that if I do the square root of 15.79 squared plus 12.04 squared, you will get 20. You will find that if I do tangent inverse of the y over the x, notice I'm putting positive 15.79 here. There's a reason for that. We'll see as time goes on. You'll get the 37 degrees. Again, I don't have those memorized. I'm literally just saying that's what the numbers are there. So you can check your work. Again, both ways work, mathematically, visually. And so make certain you're proficient at both. They'll both get you the right answer. Okay. Now we're going to do the opposite. We took the two sides of a triangle and found the hypotenuse. Now we're going to take the hypotenuse and find the two sides. This is something you have to do. You're going to see why in a second. It's just a requirement. So, I need to take this vector and make a right triangle. How do I do that? There's a couple decisions I need to make. So the question is, do I put the arrows down? In this case, the angle's down here. So we're going to make an arrow. We're going to make a right triangle. There it is in all its right triangle goodness. But we need to make those arrows. And here's all you have to figure out. Does A point to the right or to the left? It points to the right. So I make my x component point to the right. Is it pointed up or is it pointed down? It's pointed up. So I make my y component point up. If you do not make this decision about ups and downs or lefts and rights, your answer might have the wrong sign. So the math will not give you, this is something I'm going to stress you off. The math will often not tell you whether your x component is positive or negative. It won't tell you whether your y component is positive or negative. You have to assign that yourself based on the picture. That's something I'll stress to you, and you'll see again and again and again and again when you're solving problems. If you don't draw a picture, it's really easy. You might get the right answer, but you'll say it's positive when it should be negative. Or you'll say it's negative when it should be positive. And that matters a lot. It makes a big difference whether I throw a ball up or whether I throw it straight down. It makes a big difference whether I'm going to the right or whether I'm going to the left. If you're actually in a job It may seem like, oh, I just forgot the negative sign. In the real world, that matters a lot. Like, you can imagine, you don't want to go to the right when you want to go to the left. If you're think of driving your car, when you hit the gas, you want to go forward, generally. If you're going backwards, that's not going to go well for you, depending on what you're trying to do, depending on your goals. If you're trying to back out of a parking spot, you want to be in reverse. Again, direction matters. I cannot stress that enough. It may seem like just tiny little details, just a little plus or minus sign, but we're not working with just random numbers. These mean things. And in your job in the future, if you have a plus versus a minus, that could be catastrophic. That could be really bad, even though it just seems like a tiny little detail. So, great. We're going to break things into components. It's a right triangle. Already kind of showed that. And if you know how to work with triangles, you can figure this out. So, let's see. Here's a vector. I want you all to make it a triangle, and I want you all to side. You know what? I'll draw the triangle. I'm so kind. Behold, a right triangle. All right, great. I want you to decide, is the x component pointed to the right or pointed to the left? I want you to decide, does the y component point up or point down? And I have the utmost confidence that if you're given the hypotenuse and you're given this angle, see if y'all can figure out the two sides. SOHCAHTOA. So it is a vector with magnitude 12. Let's make it physics. 12 meters. Find the two sides. You know what? I'm so kind. I'll write SOHCAHTOA for you. Wow. What a generous man I am. Find the two sides. Make certain you assign whether they're positive or negative. If you made the x component to the right, good job you. If you made the y component down, good job you. That's kind of your first checkpoint. All right, so if I want to find the x component, here's something you're going to see me do in this class. Subscripts are like an adjective. So C subscript x means I have vector C and I want the x component of it. You're going to see me do these subscripts all the time. If I want the y component, I'll do CY. These subscripts can get kind of like a little crazy. Eventually, we're going to have object A. Or you know what? Let's put velocity. We're going to see V for velocity. We're going to have the velocity of object 1. Say we have multiple objects. We're going to get the x component of object 1 at the beginning. You're going to eventually see these subscripts. You can add a bunch of them. That's just a future thing that I'm just kind of letting you all know. These little subscripts are adjectives. So V1xi says the velocity of object 1 in the x direction in the beginning. I for initial. Anyhow, I mention that now because you're going to see me. It's a notation thing. And if you don't understand the notation, it's like you're not able to speak the language, and that results in all sorts of confusions and questions. So the more I say it, hopefully the easier it is. All right, so CX. It is the adjacent side. Therefore, SOHCAHTOA, I have the hypotenuse. I want the adjacent, so I'm going to use cosine. So cosine theta equals CX over C. Rearrange that, and we're going to get CX equals 12 cosine of 60. We're going to do this. You plug that in, you get a number. I'll let you do that because it's so much fun. For the y component, CY will equal 12 times sine of 60. Straightforward. You plug those in a calculator and you get the x component is 6. That's nice. The y component's not going to be nice. If you remember your unit circle, sine of 60 is square root 3 over 2. Which isn't kind. 10.4, if I just round, or 392. All right. 2 notes here. You can see if your answers make sense. 60 degrees means you pointed more down than it is to the right. 60 degrees is kind of more vertical in this case. Oh, look, our y component is more vertical. Now, this also, I almost made a mistake here. There's something very important I forgot to put in my answer. One of these answers is wrong.
The y should be negative.
the y should be negative. If you put the answer as positive, again, that is, the number will be right, the direction will not. Seems like a tiny little thing, but in the real world, whether you're going up or down, matters, especially if you're in a plane. So, it's negative 10.4, and again, I put random units here, so let's just call it meters. Beautiful. All right, that's one thing to note. The other thing to note, do not get in the bad habit of assuming that the x component is always cosine and that the y component is always sine. If you have taken physics in the past, this is really common, that the x component is cosine and the y component is sine. That is not always true. Literally the last problem on this slide will be an example where it's not, and I'll show you an example right now where it's not. Say I have a triangle where I give you this vector, and I give you that this angle is 30 degrees, and I say find the x and y component of that one. If we do this one, the y component is down, the x component is here. Let's just use the exact same numbers. 12. You know what? Let me make it 60 degrees in that case. So if I make it like this is 60 degrees, this is 12, and I say find the x and y components. In this case, my x component is the opposite side, and my y component is the adjacent side, and so it gets flipped. In this problem, right here, Cx is going to equal 12 times sine of 60. Cy is going to equal 12 times cosine of 60. Do not assume that the x is always cosine. Do not assume that the y is always sine. It's a really easy habit to get into, and it's not a good one to get into because it'll bite you in the butt if I switch things like this. And I will. Because it's going to happen. You're not always given an angle that results in the cosine and sine. So how do you decide which side's adjacent, which side's opposite? SOHCAHTOA. Always follow SOHCAHTOA. Alright? It seems like a tiny thing, but I can guarantee you, you will make a mistake of assuming that, many of you will assume that x is cosine, and you'll run into a problem and be like, oh, Dr. James warned me this would happen. And then you won't make it again. Alright, fantastic. How are we at time-wise? Alright, we got 17 minutes. Okay, adding vectors visually. This is great. It's super easy to do. We've kind of been doing it this entire time without even realizing it. We need to add, so it's one thing to do it mathematically, it's another thing to do it visually. Do them both, because this is really quick and easy. You've been doing this the entire time. Case in point, I told you vector A was 3i plus 5j. How do we draw? This is a math problem. It's a plus sign. You are adding vectors. Here, you're adding an x vector to a y vector. How did we do this? You draw the first vector. Great. There's my 3. Then you start the next vector where the other one ended. So we draw vector 5 pointed up. And the net result, we found the beginning, we found the end. We've been doing this entire time. Let's go ahead and take an example that's a little bit more weird. Let's have a vector here. Let's call this one A. We're going to have a vector B. Boom, there it is. What do these look like if I add A plus B? I draw A. I add B. That's A plus B. Super easy. If you have 3 vectors, plus, let's make C this way. Then you just take C and you put that, so here's A, here's B, here's C. My final vector, beginning, end, A plus B plus C. Ooh, spooky. All right, there you go. Something to note here. Addition, 2 plus 3 is the exact same. Oh, look, there was the vectors already there. Didn't even realize it. Addition, 2 plus 3 is the same as 3 plus 2. That also applies to vectors. So the question is, what if instead I said C plus A plus B? It's the exact same answer. I'll prove it to you. Here's C. So we're going to do it visually. So C goes down, and then A goes up, and then B goes down to the right. This is kind of messy to see, but the results beginning and the end, this and this are the exact same thing. The order doesn't matter. It's addition. Prove that for yourself. Take any 2 vectors, add them, So for example, this one here, I have R1 and R2. Try adding them both ways and you'll find you get the exact same vector either way. It's nice like that. All right. Try it out. Nice, simple. I got A, I got B, add them together. Do A plus B, or do B plus A. It doesn't matter, you get the same answer either way. 2 plus 3 is the same as 3 plus 2. And I'll draw both of them out to show it to you. All right, we'll go to like 120. This is just a matter of drawing it out. Draw an arrow that goes down to the right, then start drawing an arrow that goes up to the right, then draw an arrow from the beginning to the end. All right, we'll close this out in 5, 4, 3, 2, 1. Now, you might have been able to look at this and determine what the answer is without having drawn anything. And that is a useful skill. There is some nice symmetry here. A is pointed to the right and down. B is pointed up and to the right. You might have kind of intuitively realized that A is going just as much down as B is going up. And you might have kind of recognized those are going to cancel out. But we're going to see that. So A goes down, B goes up. Look at that. The components cancel. That's A plus B. If you're like, I prefer B plus A. Whatever. Let's do it. Up to the right. Down to the left. Oh, look at that. We get the same answer. That's B plus A. The order of math doesn't matter when it comes to addition. So, you get A. Well, if I can find my highlighter. Yay, there it is. All right, look at that. If you didn't get the right answer, that's on you because I didn't even close it. That's all right. You still get credit for responding. That's what matters, right? Okay, so, but this is a nice point that the components cancel, that if you realize the up and down components cancel, because you are actually doing something intuitively that I'm now going to show you, which is that, great, visually this is how you add vectors. Really handy, lets you check your work. Lets you see if your stuff's making sense. How do you do it mathematically? It's one thing to know A plus B goes to the right, but how much does it go to the right? If you want to get precise, pictures aren't going to give you precision. They're going to give you a sense of what will happen. If you want to get precision, that's why math exists. Math allows you to calculate things precisely, which is a necessity. Going 20 miles per hour is quite different than going 40 miles per hour, and so on and so forth. Numbers matter. So, case in point, you can't just add vectors. Let's just look at that last example. Say vector A, say this vector is 5 meters, and say this vector is 3 meters, it's also 5. This is not 10. You can't just add 5 and 5. Really easy way to remember that you can't just add these. If I have a vector to the right, that's 5, and then I add a vector to the left, that's 5. How far did I travel? I started back where it's not 10. My final location is not 10 meters away. It's right where I started. I'm 0 meters away. You can see why you can't just add the numbers willy-nilly. You have to break them into components. So that was kind of an extreme example. You have to break vectors into components to add them together. Yes, this is tedious, but there is no other way around it. You can have a software, I guess, do it for you, but it's good for you all to realize what the software is doing. Otherwise, why are they paying you a lot of money when the software is doing all the work? So, you need to know what you're doing. Otherwise, if something breaks, You're not going to know what broke. You're not going to even know what broke. You're just going to say, well, the computer gave me this. And they're going to say, well, 5 people died. And you're going to say, that sucks. I don't know. I don't know what you're going to say about that. It's not going to be good, though. So, case in point, we have this example here. We're going to make right triangles. We're going to take A and make a right triangle. We're going to take B and we're going to make a right triangle. And when we do this, we can say, hey, this is the x component of A. This is the y component of A. This is the x component of B. This is the y component of B. And you can actually see from this picture that if I add AX and BX, I get RX. If I add AY and BY, I get RY. Oh, look at that. I got the components of the big vector. So this is a nice visualization to show you why you can do this. I didn't do any math here to explain it. The picture kind of reveals it. If you take this AX and BX, it makes this big one down here. If you take this AY and this BY, it makes that one right there when you add them together. So, visual, it's nice. It helps you to kind of understand things that might be, if I just said it, it might be hard for you to believe it, but hopefully this kind of convinces you. So, how would we do this? I would have to tell you the angle of this. So I'd have to, let's just say this is 20 degrees. Let's say this is 50 degrees. You would have to get the component. If you want to solve this problem, you're going to need to find Rx. How do you find Rx? Ax plus Bx. How do you find Ry? You're going to have to do Ay plus By. And then you're going to get to do another step. How do I actually figure out how big R is? I do the square root Rx squared plus Ry squared. Each individual step here I just did is something we did in previous slides. This is putting it all together. You break things into components. We practiced that. Ax will equal this times cosine of this. Ay will equal this times sine of this because this is the adjacent, because it's the opposite. Once you find Rx and once you find Ry, how do I find the hypotenuse? Do that. This is the downside of a lecture class compared to the studio class. You all will have to practice this outside of class. Like, I'll do a little bit here. You're going to really realize that this makes sense. Oh, and one last thing. If you all want to find this angle, then sure, theta, it's going to equal tangent inverse of R, Y over R, X. All stuff we saw in previous slides. All right, we got 7 minutes. I'm keeping tabs on things. You have to practice this. Do not just assume because it makes sense when you're watching this that it's going to make sense when you solve it. Prove that assumption by actually solving problems. You will experience this at some point where you watch someone do something, you say, that makes sense, I got this, and then you never practice it, and then the assessment comes along, you try it, and you realize you didn't understand it at all. Really easy example of this. You were riding in a car, probably between the ages of 0 and 14, and you saw your parents or whoever it was driving you around driving. You said, that makes sense. They turned the wheel, they hit the gas, they hit the brakes. And then one day, if you haven't experienced, most of you all got behind the wheel of a car. And your experience was vastly different than watching someone drive a car. That is the case here. That is going to be true. All right. Hang tight, hang tight. I still got a little bit more things. All right. This is straightforward. I'm going to start this problem for you all. I know that many of you all will run into problems with this because many of my students in my studio class had problems with this and they had way more practice in class before we got to this point. So, I'm going to give you all, in the next 5 minutes, I'm not actually going to solve the entire problem. Remember, I want you all to practice these things. If I just work through this whole problem now, it might give you a false sense of security. What I am going to do, I want you all to think about this. I've got 2 vectors here. I've got a boat pulling up to the left with an angle of 12 degrees. I have on the right a boat pulling up to the right with an angle of 15 degrees. I want you all to see if you actually have a sense of how to solve this without me doing anything. So just spend like 30 seconds and think about how would I solve this. Pro tip, draw it on your paper first. If you don't draw it on your paper, you're going to have a hard time, and it's very likely you're going to make a mistake. Draw this on your paper. You don't need to draw a barge and a boat. Here's what you need to draw on your paper. Oh, the net force is adding these together. So what I'm asking for, let's call this vector A. Let's call this vector B. Do A plus B. That's what this problem's asking for. That's it. Net means total. Sum. We're going to see this word a lot in this class. Net means sum. Add these things up. So try it for a couple more seconds. We still got a few minutes. Again, I saw too many people confused in my studio. Like, I was actually surprised, which is a good sign. It means this is worth you all trying to realize, do you understand it? If you can do this, this means you understand vector addition and you're going to be set. If not, that's a good indication practice is necessary. All right, so here, this is the picture you needed to draw on your paper. You needed to draw A, and you needed to draw B. You needed to draw the angles on there, unless you have those memorized. Unless you want to be looking up, down every 5 seconds. The magnitude of A is 5,000. It says units, because I haven't taught you what newtons are yet. This, you know what? I'm going to put newtons after it, because that's the reality of what it is. We'll learn about newtons eventually. Just for now, know it's the unit for force. The answer is not 9,000. All right, so what I'm going to leave you all with is twofold. One, add these vectors visually. It's going to let you check your answer. If we just do it visually, we do vector A, we do vector V. What's the net result? It's straight up. That's going to be a helpful check later on, because if you get a vector that has an x component that's really big, you messed up. This vector, the total, A plus B, points straight up. And the next thing I'm going to mention to you all, you got to draw two triangles. So vector A, you need to draw a triangle for vector A. Vector B, you need to draw a triangle for that one. Here's your triangle. Does vector A point to the left, or does it point to the right? That matters. Vector B, does it point to the left or to the right? To the right, and they both point up. There's decisions you have to make here that aren't math-based. If you can't draw the picture right, you can't solve it with math. I can promise you that. So, there you go, y'all. That's it. If you have any questions, feel free to ask. Solve this problem by Tuesday. You got a lot of days between then and now. The quiz will open tomorrow. It'll be due a week and a day from tomorrow. Yeah, one second. Let me close the stream, unless you want to be recorded for now until the end of time. Well, until the internet crashes or when they delete the stream.